Yeah, so I changed my title, and my talk will be about inflation and string theory, and no problem. And it's based on a paper that Nima and I wrote, and also I make some remarks related to an earlier paper that we wrote with Guilherme Pimentel. So we know that inflation is the leading candidate for a theory that produces the primordial fluctuations. And the scale of inflation can be very high. I mean, it could be as high as 10 to the 14 GeV. And one question we should ask is whether there are possible signatures from string theory at these very high scales. And now the standard paradigm for inflationary models is that we start from some string theory in 10 dimensions. Then we get some gravity theory in 10 dimensions. And then we compactify that gravity theory to get the 4-dimensional theory. And from that 4-dimensional theory, we get an effective field theory for inflation, which contains the metric and some very light field, the inflaton. And the one question we should be asking is whether there is any signature in this effective theory from inflation. So that's one question. And here, I can't resist saying that the most important question of this kind is where there is a constraint on R, so the tensor to scalar ratio. I really have nothing to say about this, but we should always keep in mind that this is a very important question. And well, Ranga talked about this and saying that there are in some cases constraints. But on the other hand, we have models like the axion monodromy model proposed by Eva Silverstein and collaborators, which seems to say that there aren't any constraints. But it would be nice. I mean, if we could have told bicep string theory doesn't allow this kind of R, that would have been great. And if they don't detect R in the next 10 years and it goes down very much, and we later realize there was a constraint from string theory, also that would be very silly. So we'd better figure this out before the experiments are done. It also would be silly, yeah, to say that it is not allowed and then it, yeah. So, but I think here there is some opportunity. I mean, there is some indication that, I mean, R very large field ranges seem to have some problems. It's extremely large. Now the question is a factor of 15. So is that allowed or not? Well, as you say, there are models saying that it is allowed. There are some other arguments that at slightly different models that it's not allowed. So anyway, so that's not my talk. My main point is that in some cases, so not in those types of inflationary models, but in some other ones, there could be terms in the effective theory that arise from string effects that cannot be produced by effective field theory, and also that sometimes there are some massive string states that can leave very specific signatures. So here we are talking about strings as a theory of weakly coupled higher spin particles. Inflation, I remind you, is very weakly coupled. The effective coupling is h over m Planck. H was 10 to the 14, and m Planck, well, is much higher, 10 to the 18. So the energy scales are essentially, we have m Planck, which is fairly high, much higher than h, by about 5 or 6 orders of magnitude. And then we have the very light scalar, whose mass is a factor of epsilon, where epsilon is the slow roll parameter smaller than h. Now, the type of string theory scenario that might lead to some interesting signatures is a situation where the string scale is close to h. Now, I remind you, so close means a factor of a few from h. And since there are many orders of magnitude here, that's a rather fine-tuned situation. And I'm not saying these models are more natural, but these are the models that give more spectacular signatures. So this is similar to the large extra dimension models for physics at the LHC. So they're perhaps not the first model you might have theoretically thought about, but they are the models that give the most interesting signatures. And I'm going to call that the very string inflation, where these two scales are very close. We are putting the string scale higher than h because that corresponds to the situation where the Hagedorn temperature is bigger than the temperature in the Sitter space. Otherwise, you would have some phase transition to something else. And we don't know whether a model of this sort is possible. It seems difficult, but it might be that this difficulty is our lack of technology for understanding such models. So I'm going just to assume that there might be a model of this kind and explore some of the consequences. Now, many of the things I'm going to say are also true if we have, if this scale is not just the string scale, but it's the scale of the masses of other things, which could be, for example, Kaluza-Klein modes of the internal dimensions, or masses of other, let's say, spin zero fields, which could be partners of the inflaton if we have supersymmetry, or other scalars that we could have. And these type of models were studied in the past. They are called quasi-single field inflation, and well, they give rise to signatures I'll discuss later. Now, when we have new particles in inflationary theory, so there are two effects of the new particles. So we could have virtual effects that come from integrating these particles out classically, and they lead to new local terms in the effective action. So for example, quadratic terms which are suppressed by, again, by powers of h squared over ms, or quartic terms that lead to new interactions. Now, it's important that in this context of weakly coupled string theory, these higher derivative terms are larger than you might have naively expected if you were to put the cutoff of the, if you view gravity as an effective field theory with a cutoff at order m Planck, then those terms would be much smaller with instead here m Planck instead of ms. Okay? So we're talking about terms that are larger than the naive effective field theory description would tell you. And that this is a generic feature of string theory where you have corrections to gravity at scales lower than m Planck. So as we said, these virtual effects give extra terms in the effective action which are power law suppressed in the new scale. And then we can also have real particles that get produced during inflation and then they decay. And this gives rise to non-local terms in the effective theory. So this gives rise to terms which you cannot summarize by extra terms in the Lagrangian. And those are suppressed by Boltzmann-like factor due to the improbability of producing these massive particles. And in the case of strings, you could also produce cosmic strings which are stretched across the horizon and then get inflated by the expansion. And those are even more suppressed. So I won't discuss these ones. So let me first discuss some effects of the virtual corrections. So one interesting aspect is that there are some local corrections that should not arise in local gravity theory, so Einstein plus quantum field theory. And an example of this is the 3-graviton vertex correction. So we could imagine the interaction between 3 gravitons. In flat space, this is determined up to 2 numbers. And the 2 numbers are, well, one is the strength of gravity, so that's the typical gravitational interaction. And the other is a possible term of the form, could come from a possible term of r cubed in the action. But it's the other possible Lorentz invariant structure that we could have for the 3-graviton vertex. And the same is true when we consider the 3-graviton interaction in any maximally symmetric space, such as ADS or DS. And in a theory with a low string scale, the relative size between these two terms could be of order h to the 4th over ms, the string scale to the 4th. Okay. So now, why am I saying that this r cubed term is a signature of strings? Well, if you analyze this problem in flat space, this r cubed term leads to an asymptotic causality violation that cannot be fixed at tree level by adding any new particles with spins less or equal than 2. So in order to fix it, you really need to add many higher spin particles in such a way that the amplitude then has a Regge behavior. Okay. Now, suppose you had this 3-point function. So it's I should remind you that the gravity wave 2-point function has not yet been detected. And the 3-point function is much harder, but because gravity is weakly coupled. So we're talking about something that might be detected in the very, very far future. So now I'll discuss now the effects of new propagating particles. So first, we should discuss very light particles, especially spin 0 ones, which could give rise to very large effects. I mean, if we have a new field which survives till today, then we could get isocurvature fluctuations. And then we could also, even if they don't survive till today, they could give rise to non-Gaussianities in the squeeze limit, and that will be a special case of what we'll discuss later. And none of these two have been observed so far, but they could be observed in the near future. And those are all particles whose masses are of order square root of epsilon times h, so comparable to the inflaton. So now we'll consider massive particles whose masses are comparable to h, perhaps a little bigger. And if we create these massive particles, they get diluted rapidly by the expansion of the universe. And they could lead to interesting effects if they decay to the inflaton. And so let's first consider the effects of these particles in the 4-point function of a massless scalar field in the zeta space. And then we'll go to the inflationary situation. So we have the massive particle gets created and then decays into the inflatons. So this 4-point function depends on 4 momenta, k1, k2, k3, and k4 are the momenta of the scalars that we are going to eventually detect. And since momentum is conserved, this intermediate particle has a momentum which is just the sum of these two. Now, in order to understand the features of this formula, it's interesting to view the corrections that arise from this process as a kind of interference effect between two physically distinct processes. One is where you don't create the massive particle, and one where you create the massive particle. So you create, so you have the wave function where you didn't create the massive particle, and then you have the correction to the wave function due to the creation of the massive particle, and then you are interfering these two terms. So this point of view will be useful for understanding some features of the answer. Now, one could in principle compute this 4-point function for general momenta, and it's somewhat complicated, but it's simpler. So it's interesting to analyze the situation where the intermediate momentum is much smaller than this other momenta. So in this situation, so that in position space corresponds to the situation where we have 2 points. So these 2 points are close to each other and very far from the other 2 points. It's a bit like an operator product expansion, and we'll later see that it is indeed an operator product expansion. And the answer in this regime becomes somewhat simple. So we get powers of the ratio of this momenta to some powers here, and we'll try to understand these powers. So mu here is essentially the mass in units of h. And so we have this power law behavior in the ratios of scales. So for real mu, this is oscillatory. And these oscillations represent the oscillations of the wave function of a massive particle. So you have a massive particle, you have a factor in the wave function which is e to the I mt, where t is proper time. And these oscillations are the oscillations that get imprinted into this 4-point function. So it tells us how many oscillations happen between the moment this particle was created till it decayed, essentially. Okay, so that's that term. So here, so the log of this, the ratio of scales tells us for the number of e-folds for which this particle survive until it decay. I mentioned before so if mu could also be purely imaginary, in which case one of these 2 terms dominates, and so when this factor, the smallest value for this factor is 0, and that's what gives the biggest effect, and those are the effects for very light fields. But let's not consider those light fields for the time being. So we also get this factor, which represents Boltzmann suppression. So this is a factor. In general, it's a little more complicated, but this is the behavior for large mu. And it's a bit like a Boltzmann suppression factor, except for the factor of 2 that comes from, again, this issue that I mentioned about the interference effect. So if we ask for the probability of creating a pair, which would have to square this part of the wave function, and that would have the proper thermal factor. But since it's an interference effect, there's a factor of 2 difference. This factor of 3/2 is representing the volume dilution, so the fact that so these particles got created and survived for a while, but they're getting diluted by the expansion of the universe. If they were diluted like the volume, it would be a factor of 3, and it's a factor of 3/2 again because we are talking about the wave function and not the square of the wave function, because it's an interference effect. Finally, we have again a phase, an explicit phase, which is a function of mu, and it's calculable. We did calculate it, but I don't want to. Well, it's some simple expression in terms of gamma functions. And again, so it's a phase as we usually have phases in interference effects. And this, if you somehow found this, you would be testing some of the quantum nature of the primordial fluctuations. If this particle in the middle has spin, then you find some angular dependence on the directions of these various vectors. So there are really here 3 vectors. One is, remember that k intermediate is very small, so k1 is almost opposite to k2. So there are really 3 vectors, k1, k3, and k intermediate. And the answer depends on the various angles that occur here. And so in this way, by looking at the angular dependence, you could be seeing that you have a particle of, let's say, higher spin. So that would be the signature of string theory. And this answer, that spin dependence, is basically determined by the 2-point function of this propagating particle with spin, and is fixed by the conformal symmetry by the usual familiar form. And the overall size of this effect is very small in the 4-point function, is of the form h over m Planck square. This was the small coupling. Remember, that was very tiny. And the question is where we can find the bigger effect. And we can. So we can consider now the inflationary situation where we have a time-dependent scalar field. So we have a classical time-dependent scalar field, the inflaton. And now the same type of diagram that we considered before could be considered, and we could replace one of the quantum legs of the inflaton by this classical background field, phi dot. And if we do that, then since this one is uniform, has 0 spatial momentum, now the intermediate momentum is equal to the momentum k3. So we have only really one ratio between k3. Let's say k3 is very small and k1 is large. So we are in the regime where these two are very close and this one is separated. So in that regime, we again have a feature very similar to the one we had before. The form of the correlator is very similar to the one we had before, the same type of factors. But now we have only 1 power of h over m Planck. And roughly speaking, this prefactor here is what we get in single field inflation for the 3-point function, which corresponds to the exchange of a graviton. And in addition, we have these extra factors, which which are in general smaller factors. And again, if we have a spinning particle, we can still keep the information of the spin because we have 2 separate vectors, which are k1 and k3, and they form some angle, and the answer could depend on this angle. Now, a few words about how difficult it would be to detect this, and the short answer is very. So first, we should remember the standard 3-point function of single field inflation, which can be viewed as exchange in a graviton, and that the graviton produces a 3-point function in this limit where one momentum is very small and the other ones are larger, is called squeeze limit. And in that limit, this is of order ns minus 1, which is about 0.04, and the experimental constraint is that it's less than about 5. So we are still 2 orders of magnitude away from the 3-point function produced by the graviton. These ones produced by massive particles are, well, we have these extra factors. So remember, k3 is smaller than k1, so this is a small factor. And we have this extra, also Boltzmann suppression factor. And in principle, also, we have a factor which depends on the coupling between these massive particles and the inflaton. And the natural value of this coupling is, again, of order m Planck. Sorry, this formula is wrong. It should be lambda square m Planck. So the natural value of the coupling is 1 over m Planck. But the point is that this factor is 1 if that is a natural gravitational coupling. But this factor could be a little bigger than 1, and then we could get something bigger. So due to the presence of these small factors, the number of modes you really have to detect in order to detect something like this has to grow like the square of these factors. And so you have to detect many more primordial fluctuation modes than the ones we've detected so far. But well, one other possibility is that the interactions could be larger than gravitational, and then one could detect this earlier. So in summary, it is futuristic and lack in the sense that we need a theory where ms is similar to h, and also the ability to detect vastly more primordial fluctuation modes. This, in principle, could be done using the 21-centimeter tomography. I say in principle because there are some foregrounds which are very large, and it's an experimental issue of whether it can or cannot be done. But in any case, we'll first would detect some non-Gaussianity, and then we'll go to the squeeze limit and read off the spectrum of particles during inflation. Now here we discuss just the exchange of a single particle, but there are many situations where the inflaton doesn't couple to a single particle, but couples to a pair of particles. which would have Higgs field, gauge fields, or fermions of the standard model, and due to the gauge symmetries, they would couple to pairs. And this also give rise to similar factors, except that now the decay is a little faster. It's a factor of 3 instead of 3/2. For 2 particles of mass mu, we get an expression roughly of this form. Okay, and also there are extra factors of these small couplings. So now I'll discuss some conceptual aspects of this calculation. So the first one is that what we are doing here is trying to find the signature of new particles during inflation. And if we were doing collider physics, so if we were doing a scattering experiment instead of a cosmological experiment, we would look at peaks in the invariant mass distribution. So we have a collision, and then we look at some number of the decay products. We form the invariant mass, and we would have these peaks. And this is a famous example. And what we're trying to do here is the cosmological collider physics. So we have some observables, which are the primordial fluctuations, so the spectrum of the distribution of primordial fluctuation modes, and from the statistics of these modes, we like to extract the particles, and we extract them by looking at we take those, for example, the 3-point function, and we look at it in terms of this as a function of L, which is the log of the ratio of the 2 scales, and we could Fourier transform it, and peaks in that Fourier transform detect the spectrum of particles. And the spin will be the angular dependence. Now, you heard in Trivia's talk that the Sitter isometries and conformal symmetry are very closely related, and so if we have the Sitter space, so we know that first, and we consider a correlation function of any 4-dimensional, of an operator in a 4-dimensional theory, which is not necessarily conformal, it's a 4-dimensional theory, then these correlators are invariant under the Sitter isometries. And at late times, the Sitter isometries act on X as conformal symmetries. That's a familiar fact. So if we consider a quantum field theory in a fixed de Sitter background, we can often, let me see, at late times, we can expand these operators in terms of powers of eta and some coefficients, which are other operators which depend only on X. And then the de Sitter isometries imply that these operators transform. So the Sitter isometries, together with the invariance of this operator, implies that these O3s transform as primaries, as primary operators with dimension deltas. And these deltas are the quasi-normal frequencies in the de Sitter static patch. So this is how these are the spectrum of dimensions that appear here, have to do with these quasi-normal frequencies in the static patch. So this is I'm not sure if this was proven completely, but certainly we observed it in all the cases, and you can sort of understand it in a hand-waving way. Okay. Of course, these facts are necessary for DSCFT, but this is independent of DSCFT. These facts are necessary conditions for DSCFT, but they're independent. So the squeeze limit corresponds to an operator product expansion, where we are exchanging a bunch of these 3-dimensional operators, and the powers that appear again are the quasi-normal modes in the Sitter. So by looking at this observable in the 3-point functions, we can read off the spectrum of quasi-normal modes, and therefore read off the spectrum of excitations in the static patch. So in conclusion, so if the string scale was similar to the Hubble scale, then there could be direct signals of string theory in the primordial fluctuations. And the signals are, first of all, local effects, terms in the classical Lagrangian which are not field theoretic in origin, or non-local effects that correspond to real particle production with spins bigger than 2. Of course, we could also have everything that I said also applies for spin less than 2. And requires lag to be observable, but there are also interesting theoretical aspects in how the signal of this particle is encoded in the primordial fluctuations. So we saw this connection between quasi-normal frequencies and the dimensions of operators and the squeeze limit of cosmological correlators. And this is a small step into decoding the cosmological hologram, right? So how things are encoded in the fluctuations. Thank you. Yeah, Sandeep.
Thank you. For questions? So
Yeah.
Or just from the graviton. Because it's an interference term, could you think conceptually at least of a Bell-type experiment on the sky that would tell us that the origins of quantum perturbations were quantum?
Yeah, one can certainly think about the Bell type experiment, and I would refer you to a talk I gave in Stanford some years ago. But a Bell inequality is much stronger, so it's a much stronger requirement, because you really need to be able to do separated measurements and choose the the projections of the spin and so on separately. And you can think about that, but it requires a more elaborate and baroque scenario. So, but yeah, you can do that. But of course, in ordinary quantum mechanics, we understood that quantum mechanics was correct much before the Bell experiment was done, right? There are lots of evidences that. So this is like the Young double slit experiment. That's analogous to that. Yeah.
Question?
Massimo? Yeah, very good. Yeah, I forgot to mention that. Yeah, so this R cube term would be forbidden if the theory is supersymmetric at the Planck scale. So in order for this term to be present, the theory has to be completely non-supersymmetric. So this term is only present if the theory is completely non-supersymmetric. So for example, if we look at the ordinary string theories we know, this term is present in the bosonic string, but it's not present in the heterotic string or in the type 2 string. Yeah.
How do you distinguish between the R cube term and R to the fourth term with some background? I mean, one R being used as a background from inflation.
Yeah, so here we're looking at the on-shell coupling between the three, and I just don't distinguish between them. So it's whatever coupling you have between the three.
How would this be a signature of, let's say, string theory, or just ordinary, let's say, if you had a scalar field, you integrate it out, there would be other projections on R to the fourth and higher?
Yes.
They would induce an R cube term in the background. How would you distinguish?
Well, first of all, we are talking about the on-shell coupling between the three gravitons. So I don't care how it got induced, but we have this on-shell coupling between the gravitons, and that's what leads to this causality constraint, for example, we were discussing. So yeah, so we don't care. So if you notice, however, that the term we are talking about arises in the classical theory. So if it arises by integrating out many fields, you have to integrate out a large number of fields so that it gives rise to a classical effect, right? So we're talking about an effect which is larger than what you get by integrating out just, let's say, a single field. But this is the type of term we get in bosonic string theory. We get this term with the properties I'm just stating. So this term with a coefficient much larger than we would get by integrating out a finite number of fields.